Welcome back to Students Teach Orgo. In this video, we're going to begin with an introduction to organometallic chemistry. So far in organic chemistry, we've been dealing with atoms that generally follow the octet rule, right? So nitrogen and oxygen and carbon all prefer to have 8 valence electrons. However, when we start looking at organometallic complexes, we'll start introducing some metals. These are the transition metals, found a little bit to the left in the periodic table, that instead follow this 18 electron rule. In comparison to the octet rule, the 18 electron rule is a little more loose, meaning that it's common to find organometallic complexes that have 16 or maybe even 14 electrons. In this video today, it's really common to use the term ligand to describe anything that's bound to a metal. In organic chemistry too, some of the most common questions they'll ask you on a test related to organometallic chemistry relate to the oxidation state of the metal and the electron count. So those are some important terms to know, and we'll also use this d to the n notation, which will refer to the number of electrons that the metal specifically contributes to the complex. And then we can use that n number, right? So like if it was d to the 8, that means the metal's contributing 8 electrons. We can use that number and then add that with the number of electrons the ligands contribute to find the total electrons in that complex. And on this next slide, I'll give you a little equation that shows that. When we're talking about organometallic chemistry, the difference between L-type ligands and X-type ligands becomes very, very important. So as we can see here, what differs between an L-type and an X-type ligand is that if an L-type ligand dissociates from the metal, it is neutral. However, if an X-type ligand dissociates from the ligand, it's going to have a negative charge associated with it. So that's just words. Let's see if I can draw out a little example here. So I'm just going to draw this M right here to represent any one of these transition metals. Now let's say that we take this nitrogen right here, right? And we form a bond with the nitrogen. So now this is an organometallic complex. If this nitrogen atom were to dissociate, we could show that by putting the electrons onto the nitrogen. Now once this nitrogen has the electrons on it, it's going to look just like this with the lone pair. And in that case, nitrogen doesn't have a charge, so it would be an L-type ligand. Let's use the example of carbon monoxide here, because that's another really common one. If we see an M that is bound to a C, which is triple bonded to an O. Now, in this case, you might think, well, hey, if we put the electrons onto here, carbon would have a negative charge, so why is this an L-type ligand? Well, it's important to remember that the oxygen would also have a plus charge. So that means when dissociated, it's still neutral. Another thing that's interesting is that metals can bind to aromatic or pi systems of electrons. So for a case like benzene, let's say, we're not going to do the same thing where we take these electrons and put it somewhere. That's not what we're going to do. Because when the metal binds to the pi system, it's not binding with one carbon in particular. It's binding to the whole system. And so any time that a metal binds to a pi system or an aromatic compound, it's going to be an L-type ligand, as long as there's no charge. However, the difference could be seen here with X-type ligands, right? So if we had a metal that was bound to, let's say, a bromine, when the bromine goes to dissociate, we'd put the electrons on the bromine and get Br-, which would be a negative charge. So that's why bromine would be an X-type ligand. Another ligand that's kind of weird is hydride right here, right? So normally we think about H+ floating around in solution, right? That would be like, make something acidic. Metals are very, very not electronegative, to the point where these transition metals are actually less electronegative than hydrogen. So if we have a metal that's bonded to a hydrogen, if this complex were to dissociate, these electrons would actually go with the hydrogen and make H-, which is something we haven't seen a ton before, but it's good to, keep that in mind. Another thing is that if you have a metal that's bound to any carbon chain, right? So let's say that's our chain of carbons. If we were to dissociate this ligand, the electrons would go onto that carbon and make a carbanion. So for any alkyl group, we're going to have an X-type ligand. It's also important to note that ligands can be combinations of L and X type, right? So in this case, we have a metal that's bound to this aromatic system of this 5-membered ring. We can see that though, because there's a negative charge, that makes it 1 part X type. But because there's these 2 double bonds that would be neutral if they left, it's 2 parts L type. So this would be an L2X ligand. Over here again, we can see that the double bond part would be neutral when it dissociates, but there's a negative charge here. And so this would be an LX ligand. Anyways, really important. Over here are all of the equations that you'll ever need to get any electron count questions or oxidation state questions correct. So if a question asks you to find the oxidation state of a metal, you just need to count up the number of X-type ligands. So we just talked about how we can identify the X-type ligands. You count up the number of X-type ligands attached to the metal and add an overall charge. So sometimes the metals have an overall charge and sometimes they don't. And I'll show an example here in a little bit that gives an example of what the overall charge would look like. This doesn't happen for every question. N would be the number of electrons that the metal contributes, right? We're talking about that D to the N notation. So to find N, we would first find the valence electrons in the metal in the ground state. Well, how do we do that? In order to do that, we go to the periodic table and we look at the group that the metal is in. So let's say we had cobalt and we were trying to find out the number of valence electrons that metal has in the ground state. We would go to look at its group number, which is group number 9. And so that would be a 9 for the electrons in the ground state. We would subtract the number of X-type ligands, and then we would subtract the overall charge, again, if it's applicable, if it's there. To find the electron count of the entire complex, we're going to take that N number, which is, remember, the number of electrons the metal contributes, and we're going to add that to 2 times the number of all the ligands. Now, I should say that this isn't necessarily completely true, because remember this ligand benzene over here? It was binding to the aromatic system, but there's 6 electrons in that aromatic system of benzene. So in this case, you would actually add 6 for benzene, and you do 2 for all the other ligands, right? So you'd most of the ligands here contribute 2 electrons. The only examples here, I think I've denoted with 6 electrons. This would be 6 electrons, 4 electrons, and you can just find that by counting up the amount of electrons in that pi or aromatic system. So what we can do is combine this equation and we can add it with this one to produce this one down here. And so this is a shortcut that kind of, goes through both of them. If we find the valence electrons in the metal ground state using the periodic table, and then we add 1 for each X-type ligand, but then multiply by 2 for all the L-type ligands. And again, just remember, be careful of ligands that contribute more than 2 electrons. And then we subtract the overall charge. That will, in one equation, give us the total electron count for a complex. So I have this slide here just to clear up a really confusing aspect of this whole organometallic complex chemistry. I talked before about how a metal can bind to the pi system of a ligand. And in this case, it's contributing 6 electrons because there are 6 electrons that participate in the aromaticity. A metal could also bind to a single carbon in benzene. So in this case, this would be an this would be an L-type ligand because the metal is binding to the pi system. But if the metal binds to a specific carbon, this is now an X-type ligand because now, using our curved arrows, we could show the electrons going onto that carbon if this ligand was to dissociate, having a negative charge there. So that's an important thing to watch out for. For this example in the middle here with ferrocene, they show that the compound is aromatic by giving us this ring here, but they don't show us any of the charges or what that looks like. So in this case, we have to use some of the rules that we learned in aromaticity to say that in order to have a 5-membered ring that is aromatic, we would have to have something that looks like this, because that would follow Huckel's 4n plus 2 rule. 6 electrons would be considered aromatic, and every single one of these carbons is sp2 hybridized. So in this case, all of these 5-membered rings would be this L2X type ligand, because it's an X type because there's one negative charge, but then L2 because of these 2 double bonds, those 4 electrons, that would be neutral when dissociated. And so down here, I think I explained before, again, this would be an LX because X because of the negative charge, L because of the double bond that will remain neutral. So now we'll look at a practice question for determining the oxidation state and electron count for a complex. So this is a compound with rhodium, which is in the 9th group of the periodic table. And we got 3 questions here, right? What's the oxidation state? What's the number of electrons the metal contributes, which would be the d to the n? And then what's the total electron count? So if you would like to try this question by yourself, feel free to pause the video right now. I'm going to go forward and show you the equations to determine the right answer here. So this would be rhodium 1. Well, how do we figure that out? We need to find the number of X-type ligands. Would PPH3 be a X-type ligand? Well, if we took this bond and put it on the phosphorus atom, phosphorus is actually right below nitrogen in the periodic table. And we know that nitrogen usually has the lone pair and then binds to 3 things kind of like that. So if we have this phosphorus atom that's bound to the 3 phenyl groups with a lone pair, that's going to be neutral. So this is an L-type ligand. So we're not going to count that in this oxidation state number. Carbon monoxide, like I talked about before, is also an L-type ligand, right? Because the carbon would have a negative charge, the oxygen would have a positive charge, and so this is neutral if it dissociated. So this is L, not X. However, hydrogen, remember, because it's more electronegative than the metal, would actually become a hydride ion if it dissociated. So this is the only X-type ligand. So we would just have 1 for one X-type ligand, and there's no overall charge here, so it would be rhodium 1. Then we'd look at the number of electrons the metal contributes. So rhodium is in the 9th group here. So the valence electrons in the metal ground state would be 9. We have 1 X-type ligand, as we talked about before, so that would be -1. And there's no overall charge, so that's just going to remain 0. So we can see that this would be a d to the 8 to show that this metal contributes 8 electrons. And now we can go and find the total amount of electrons in this complex by taking that 8 from the d to the n. So that 8 comes from right there. And then 2 times all of the ligands. So there's 1, 2, 3, 4, 5 ligands. So that's where we get the 5 right there. Multiply that by 2 to get 10. 10 plus 8. This complex has an electron count of 18. Got another practice question here. Remember how earlier I was talking about overall charge? This is an example of an organometallic complex with an overall charge. We can see that the entire complex has an overall charge of +3. So again, if you'd like to try this question by yourself, feel free to pause the video and do that now. I'm going to show the calculations that would lead to the right answer here. So to find the oxidation state of cobalt, in this case, we need to find the X-type ligands first. In this case, if we dissociated one of the ligands, nitrogen is neutral when it's bound to 3 things and has a lone pair. So in this case, none of the ligands are X-type, so that's going to be a big fat 0. However, remember that the oxidation state equation does take into account overall charge. So we have an overall charge of 3 plus, so we have to add in 3 there, meaning that right now we have cobalt 3. For d to the n, we look at the group that cobalt is in. Again, it's in group 9, just like rhodium. So it's going to have 9 valence electrons in the metal's ground state. There's no X-type ligands, so we subtract 0. There is an overall charge, so we subtract 3 because the overall charge is plus 3, giving us that this cobalt is contributing 6 electrons. Then we can put it all together to find the electron count of the entire complex. We take the 6 electrons that cobalt is contributing, plus 2 times all 6 of the ligands. Each one of these nitrogen bonds to the cobalt is 2 electrons, so 2 times 6. And when we add 12 with 16, we get 18 electrons. And there's the shortcut method down there. I've got one more practice question for you today. In this case, we're looking at the Grubbs catalyst. It's a ruthenium catalyst that is catalyzes olefin metathesis, which we'll talk about later in this section. Before you try the question on by yourself, I just want to point out this tricky carbene here. So we can see that right here we have the ruthenium atom has a double bond with a carbon atom. And I know earlier on I said that anytime a metal is attached to any carbon compound, that when it dissociates, we'd get a carbanion, right? The C-. However, a carbene is a weird thing in chemistry where we have a carbon that has 2 bonds and a lone pair. And this actually fulfills the carbon's octet. When a carbene is associated with a metal, it's actually an L-type ligand because this compound right here would be neutral when it dissociates. So with that, feel free to pause the video and try the practice question. I'm going to move on. So when we go to try to find the oxidation state of the metal, we have to count up the X-type ligands. So remember, just like I talked about, this carbene is not an X-type. Sorry, that's really confusing. Not X-type. It is in fact an L-type. There we go. So that's not going to count. However, and we talked about phosphorus too. Phosphorus, you'd put the electrons on there, and that's going to be neutral if it dissociated. These chlorine atoms, however, if they dissociated, they would become Cl-. So these 2 chlorines are both X-type ligands. So we've got 2 X-type ligands. There's no overall charge in this one, so we would have ruthenium 2. Next, we'd look at the number of electrons the ruthenium contributes. Ruthenium is in group 8, so it's going to have 8 electrons in its ground state. We subtract 2 because there's 2 X-type ligands, no overall charge, so the ruthenium is contributing 6 electrons. And then when we go to find the entire electron count, we take the 6 electrons that the ruthenium is contributing, and then 2 times 5, because we've got 5 ligands in total. 1, 2, 3, 4, 5. Each one of those 5 ligands is contributing 2 electrons, and so that'll give us 16.